So our discussion now will be looking at hexoses. Very important. What should you remember about hexoses? Just like any other monosaccharide, these hexoses, they can either have an aldehyde or a keto. Remember, they can either have aldehyde, which we said is carbon, double bonded to oxygen, single bonded to hydrogen. Or they can have a keto. A keto, carbon, double bonded to oxygen, single bonded to carbon, and another carbon. That's what we should know about hexoses. In this course, we shall focus on 3 examples of hexoses so that you understand their structures, because understanding the structure is very cardinal in the understanding of metabolic reactions that occurs in carbohydrates. So we shall look at glucose. We shall look at galactose and fructose. There's something I need to mention to you, very important. When you go to the books will not give you a clue on how to remember the straight chain structures of these monosaccharides. The method I'm going to use right now will help you to understand their structures and remember them at any time. So please, I want you to understand the point very well. The sugars you are seeing on the board, the ones I've written here, glucose, galactose, fructose, we are calling them hexoses because they all have 6 carbon atoms. And if they have 6 carbon atoms, what will be their formula? Remember the general formula in the introduction, CH2ON. So if we put 6 there, the formula will become C6H12O6. You see why I told you that hexoses are physiologically important in the human body? Remember when we did photosynthesis in plants? Remember when we did respiration? We used glucose. And what is the formula that we use to write all the time? C6H12O6. If you are asked to draw the straight chain of the 3 sugars, you should remember that because they are C6H12O6, their straight chain is similar across. They have 6 carbon atoms. 1, 2, 3, 4, 5, 6. And this one, it's the same. 1, 2, 3, 4, 5, 6. This one is the same. 1, 2, 3, 4, 5, 6. And it is always important for you to remember numbering them. The carbon atoms are numbered starting from the top. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. If I was to ask you to draw any of the sugars, just you remembering the straight chain and the numbering, you get some marks. So this is how you should remember them. Of the 3, 2 are aldoses. Glucose and galactose, they are made up of aldehyde functional group. But fructose is made up of a keto. Remember the structures. This is the structure of an aldehyde. And this is the structure of a keto. So glucose and galactose, they are made up of aldehyde, meaning they are reducing sugars. Fructose is made up of a keto, meaning it's an example of a non-reducing sugar. Since we are saying the 2 are made up of aldehyde, we need to know where they are located. For glucose and galactose, it's on carbon number 1. And already, after doing that, you can see that I have generated the structure of an aldehyde there, this one. Even on galactose, it's on number 1. For fructose, number 2, you can see that this structure is a keto. The next thing you need to remember is the fact that All the 3 sugars on carbon number 6, they are attached to CH2OH, CH2OH, CH2OH. When you reach this point, the only structure I will ask you to know by heart, if possible memorize, is the structure of glucose. Because when you know this, you can draw any hexos from this one. It's the starting point. And for glucose, on carbon number 2, on your right side, there is OH attached. On your left, there is H. On carbon number 3, there is H there. There is OH. I know you ask me to say, why are you writing HO? I am writing HO because what bonds to carbon is oxygen. And if I'm writing OH on your left, if I write OH, it will change. Hydrogen instead will be bonding to carbon, which is incorrect. On number 4, OH, H, then OH, H. When you remember this structure, it will be easy for you to draw galactose and fructose. Why am I saying so? The structure of glucose doesn't very much differ from galactose. The difference is only on carbon number 4. What is the difference? On carbon number 4 of glucose, OH is on your right side, H is on your left. But when we come to galactose, it exchanges. OH comes on the left, H on the right. But the rest is the same as glucose. Meaning, the same way you've drawn glucose, that's how you should finish for galactose. On number 2, see what is there, OH, H. Number 3, H, HO. Number 5, OH, H. You have completed the structure of galactose. If we go to fructose, for fructose, what it has on number 6, CH2OH, is what it possesses on number 1. Meaning that fructose is different from glucose just on carbon number 1 and number 2. But the rest is the same as glucose. What does it mean, same as glucose? The same way it is on number 3. What do we have there? H, OH, OH, H, OH, H. You have completed the structure of the 3 important hexoses. Why am I showing you the structures like this? You need to understand the structures because we shall progress to other groups of carbohydrates. We shall progress to disaccharides, oligosaccharides, and poly. If you don't understand the structures of monosaccharides, it will be very difficult for you to understand their structures. So now that we have drawn them, there is a statement, very important statement that I want to make about the hexoses. What is this important statement? These hexoses, they have straight chain structure, which I've drawn here, when they are in an environment without water. That's when they look like this. The moment you expose them to water, they form what is called ring structures. They become rings in the presence of water. How do they fold? For me to demonstrate how they fold to form ring structures, I'm going to use glucose as an example. So glucose will be the example that I'll use in order to demonstrate to you what happens when these hexoses are exposed to water. So in the presence of water, which we call H2O, and when I say H2O, from lecture 1, remember our first lecture on water and its chemistry? What did we say is the structure of water? When we say H2O, you should remember water is oxygen bonding to partially positive hydrogen, bonding to partially positive hydrogen, and we have lone pairs of electrons there, plus an angle of bonding. The pairs, partially negative, partially negative. That's what we discussed in the when we are doing water and its chemistry. So remember this structure because we shall use it in order to demonstrate how glucose, when exposed to water, folds to form a ring structure. So when glucose is exposed to water, carbon number 1 reacts with carbon number 5 as the sugar tries to fold. What does this mean? Let me demonstrate. When this reaction is about to occur, the structure changes. What starts is carbon number 6. And we know in carbon number 6 we have CH2OH, this one. Then after that, this one bonds to carbon number 5, makes a corner to carbon number 4, a corner to carbon number 3, a corner to number 2, and finally to number 1. And on number 1 we have an aldehyde. Why does the sugar fold like that? Because when it folds like that, the essence is to position carbon number 1 close to carbon number 5. Because we are saying that what reacts is carbon number 1 and number 5. And when they are positioned like that, when carbon number 5 is positioned close to number 1, because on number 5 we had OH and H. This is what is here. Number 5, OH, H. This is there. On number 1, aldehyde, there. I know you want me to show you the other parts here, but we are not interested for now because what is reacting is carbon number 5 and carbon number 1. So we need to understand what is happening at number 5 and number 1. In the presence of water, water facilitates cutting of the hydrogen on carbon number 5. So this hydrogen there is cut, leaving this part negatively charged. And when this hydrogen is cut, this proton, when it is cut from there, the proton, because it is positively charged, it goes and bonds to one of the negative charges of water molecule there. Let me use the same color. And water transports this proton. And this proton goes and bonds to that oxygen, leading to reactions that we can't explain now. This is pure electrochemistry. And the reactions leads to breaking of this bond so that it remains a single bond. And then this negative charged oxygen reacts with the carbon there. When that happens, there is a rearrangement of the structure. And this rearrangement of the structure leads to something like this. Quite all right, carbon number 6 with CH2OH bonding to carbon number 5. And when you removed OH there, what remained is the oxygen, that one, that's the one I'm showing, which we said reacted with carbon number 1 there. And of course here we have number 4, number 3, number 2 bonding to 1. On number 1, there is that H and there is the OH. Here, there is that H that remained, this one. That is what we call structural rearrangement. Now, you should observe something very important here. On carbon number 1, I have decided to show OH below. Otherwise, you can as well decide to show on carbon number 1, OH can be up while H down. But when you do that, you should remember that the name of the sugar changes. When you put on carbon number 1, OH down and H up, this kind of sugar is called alpha glucose. When you decide to swap, OH goes up, H down, the name of the sugar is beta glucose. We haven't completed the structure. Why? Because we don't know. We haven't shown the location of OH and H on carbon number 2, 3, and 4. Again, the books will not give you information on how to know whether to put OH up or down on carbon number 2, 3, and 4. I'll give you a clue that I want you to use, and the clue is that for you to know where to put OH and H on carbon number 2, 3, and 4, you should use your initial straight chain structure. For example, on number 2, this one, where are we supposed to put OH? Is it up or down? The clue I'll give you is, if you see in a straight chain, OH is located on your right side, put it down in the ring form. If it's on your left, put it up the other way. So right, down, left, up. Let's give an example. Carbon number 2. Where is OH located in the straight chain? It's on your right. And we said the right should be down. So OH will be shown down, H up. On number 4 or 3, where is OH on your left? So because it is on your left, we should put it up, then H down. On number 4, where is OH on your right? So it should be down and H up. We have completed the structure of glucose in its ring form. We don't like wasting time in biochemistry. Sometimes the way we draw this structure is like this. Because we know that in biochemistry, every corner represents carbon. When you want to draw this structure, we just do this. We draw carbon number 6, and then we just make corners. In doing that, you still know that this is number 1, number 2, number 3, number 4, 5, and 6. Then just put lines in order to indicate the locations of OH and H. That's what we show. Go and practice the same process I've explained on galactose and fructose. You should remember one important thing before I summarize monosaccharides. I gave you 3 examples of monosaccharides that we shall look at: glucose, galactose, and fructose. The 3 sugars you are seeing there, if you look at them very well, they have the same chemical formula. And their chemical formula is C6H12 or 6. So the 3 sugars you are seeing here, they differ in structure. When you look at them, they differ in structure. Remember I said what? Glucose differs from galactose on carbon number 4. Glucose differs from fructose on carbon number 1 and 2. But they have the same chemical formula. So, sugars with the same formula but differ in structure are called isomers. So isomers are sugars with the same chemical formula like glucose, galactose, and fructose, but when you look at their structural configuration, they are totally different. That's what we call isomers. Having understood the structures of the 3 sugars, we are now ready to proceed to the next group of carbohydrates, which is disaccharides.